Welcome back to another video. It's your favorite math professor here, Dr. Tarcia Hubert. And in this video, we are going to be talking about the least squares regression. So recall from a previous video, we talked about scatter diagrams, and we talked about trying to find a linear pattern through those scatter diagrams, trying to determine if there is a linear relationship between your x and your y variable. Well, we're going to dive a little bit deeper into that concept in this video, talking about linear squares regression. So I'm going to start off with this example here. It says, draw a scatter diagram to represent the data below. So if I have these data points, these are my x and these are my y's, and I wanted to draw a scatter diagram to represent those points, it will look something like this. All right. So I have each and every point. Those are 5 points represented here. And what I want to look for is a linear pattern through this scatter diagram. And you can see it does follow a linear pattern. And so once we recognize that our graph follows a linear pattern, then what we want to do is we want to try to find a line that fits the data. You may have heard it called the line of best fit. And basically it is a line that fits as close to the data points as possible. And there are multiple ways that we can find that line. But for this particular example, we just want to pick 2 points in the scatter diagram and find the equation of the line that passes through those 2 points. So you could pick any 2 points, but what I'm going to do is I'm going to pick the lowest point here, which is 3, 4, and the biggest point here, which is 8, 14. And in order to find the equation through those lines, we have to recall some formulas that we used in algebra. The first one is the slope formula, which is given by y2 minus y1 over x2 minus x1. That is a typo. That should say x1 right there. I will fix that in a moment. And the second formula is given the point slope formula, which should be y minus y1 equal to m times x minus x1. So let me make this correction right here. This x2 right here should be an x1. So that should be x2 minus x1. So if I use these 2 points, 3, 4, and this biggest point here, 8, 14, then I will call one of these x1, y1, and I will call the other one x2, y2. And then first thing I will want to find is the slope. So the slope is equal to y2, which is our 14, minus y1, which is our 4, over x2, which is our 8, minus x1, which is our 3. So that would be 10 over 5, which is equal to 2. So our slope would be equal to 2. Now we would find the equation of the line by plugging it into the second formula, which is the point slope formula. So we would do y minus y1. Our y1 is 4, is equal to m, which we now know is 2, times x minus x1, which is 3. And in order to finish solving this, we would distribute the 2. And that will give us y minus 4 equal to 2 times x is 2x, and 2 times 3 is 6. So 2x minus 6. Then we would move the 4 over by adding 4 to both sides. And that would give us y equal to 2x minus 2. And so that right there would be the equation of the line that passes through those points. And I am going to just kind of sketch a line from that point to that point. And you can't see it because it's white. Let me change the color of it. Black. Let me do it again. So sketch a line from that point to that point, and that is what that trend line of best fit would look like, right? And so that is one way to find a line that kind of fits those points. As you can see, it passes through all of the points except this one. And one thing that we use this line for is to make predictions about other values that may not be observed, okay? So for example, we don't have an observed value at 6. So we can use this line to make a prediction of what the y value would be when the x is 6. And we could say it would be 10, all right? And that is how we use it now. As you notice, that not every point will fit on this line, and so we end up getting what's called an error, or also known as the residual. And so what we want to do is we want to use that equation that we just had, y equal 2x minus 2, to predict y when x is 5. And so the way we would do that is we will replace x with 5. And we will say y is equal to 10 minus 2, because 2 times 5 is 10. 10 minus 2 is 8. So y is equal to 8. So this is how we would use that equation that we just came up with, the line of best fit, to predict the value for x, for y, when you're given a certain value of x. So we predict that y will be 8 when x is 5. However, as we can see in our data, our observed data for 5 is 7. And so the point I'm trying to make here is that your prediction may not always be accurate. You may end up with a little error, and that error is called the residual. All right, the residual is the difference between the observed value of y and the predicted value of y. And it's written like this: residual is equal to observed value of y minus predicted value of y. So for that last problem that we just did, our residual would be equal to, our observed value of y was 7, but our predicted value of y was 8. So it would be 7 minus 8, which is -1. So that's how you would calculate the residual, is you would subtract the observed value, which is the actual value, minus the predicted value. And that just goes to show you that your line of best fit, the line that you use to predict the value, is not 100% accurate, okay? It just gives you a way to make an estimate of what those values are. And so we end up with a method that creates the best line for us, and it's called the least squares regression. And this line is the line that minimizes the sum of the squared errors. So basically the sum of the residuals. It minimizes those errors, and the line is found by doing this formula over here. We use y hat instead of y. Y hat, it means the predicted y. With this little, looks like a caret key on top of it. This is y hat, and it's found by doing b1 times x plus b naught. b1 is found by doing your correlation coefficient times your standard deviation of y divided by your standard deviation of x. And then your b naught is found by doing the mean of y minus that b1 you found here times the mean of x. Now recall that this equation of the line is in mx plus b form, mx plus b, where your m, which is b1 here, is your slope, and your b naught here is your y-intercept, okay? So we're going to keep that in mind when we are interpreting our least squares regression line. So here's an example. For the data set below, determine the least squares regression given the following information. So for this problem, it actually gives us the mean, it gives us the standard deviation of x, it gives us the mean of y and the standard deviation of y, and it also gives us r, our correlation coefficient. And so what we want to do is we want to find the least squares regression line. And so recall, this is the formula for the least squares regression line, but you also have a formula for b1, which is found here, and you have a formula for b naught. All right, so what we want to do is we want to calculate each of those. So b1 is going to be equal to r, which is your 0.957241 times your standard deviation of y, which is 0.461519, divided by your standard deviation of x, which is your 3.03315. And if you calculate all of that, you end up getting 0.14565 218. So when you calculate it, you just do the 0.957241 times 0.461519 divided by 3.03315. And that is what you get for B1. Now we need to calculate B0, and that's going to be the mean of Y, which is 2.04, minus your B1, which is at 0.14565. That's a 6, 2, and some more numbers, times your X, the mean of X, which is 6.2. And I ran out of space, so I had to write that at the bottom. But that is times, that value. So you get 2.014 minus 0.14565,218 times 6.2. And if you work all of that out, you end up getting your B0 to equal, it ends up being 1.13695,649, which is a long strand of numbers, and I have numbers up here that are long. I'm just going to round these to 4 decimal places. And if you're doing homework in my math lab, it'll tell you how many decimal places to round it to. So this would be 0.1457. And B0 would be 1.1370 if you round it to 4 decimal places. And so your equation ends up being Y hat equal to B1, which is 0.1457x, plus B0, which is 1.1370. And this ends up being the equation of your least squares regression line. So that's Y hat equal 0.1457 plus 1.1370. Now, when you're interpreting these, you have to remember that slope is rise over run, or change in Y over change in X. So that number that's in front of the X is going to be your slope, and that other number is going to be your y-intercept, and that's the point where the graph intersects the vertical axis, which is found by letting x equal 0. So another way to say that is that we interpret the y-intercept as the response variable when the value of the explanatory variable is 0. So you have to think about the context. In our example, there is no context, it's just numbers. But think about the context of what it means for the explanatory variable to be 0. And then we have to be careful that we do not make predictions for values of the explanatory variable that are outside the scope of the model, meaning they are bigger than our last observed value and smaller than our smallest observed value. So you only want to make predictions with inside the model. All right, and the last thing we want to be able to do is compute the sum of the squared residuals. And we're going to do this from the last example, the one where we just found the regression line, the least squares regression line. So I am in Excel, and what I want to do here is I want to show you how to calculate the sum of the residuals in Excel. And so the first thing I need is my predicted value y hat. I can't put the hat on top in here, so I'm just going to write that little caret key afterwards. And y hat is found by using that equation that we just had. So remember that equation was the equation that we just found. It was 0.1457x plus 1.1370. That was our equation. And so we want to use that to find our predicted value for each x. So I'm going to do equal to 0.1457 times my x value over here plus the 1.1370. And that's going to give me my predicted value for each of my data points. And I take that square and drag it to the bottom. And then I want to subtract y minus y hat. So I'm going to do equal this minus this. And I'm going to take that and drag it down. That gives me my y minus y hat. And then I'm going to square each of those. So I'm going to say equal this times this. And I'm going to take that and drag it down. And I want to take the sum of those. I want to do the sum of each of these.